Applications of GIS. Objectives. In this chapter, we will discuss about various applications of GIS, that is, application of GIS, inventory application, analysis application, management application, 5 M's, GIS in environment, GIS in forestry, GIS in fire prevention, GIS used in vegetation management, GIS in education and training, GIS health management, GIS in hydrology, GIS in geology, GIS in agriculture, GIS in archaeology and GIS in fishery. Applications of GIS. An important distinction between GIS application is whether the geographic phenomena studied are man-made or natural. Clearly, setting up a cadastral information system or using GIS to urban planning purposes involves the study of man-made things, mostly the parcels of roads, sidewalks and at large scale suburbs and transportation routes are all man-made. Those entities often have clear-cut boundaries. On the other hand, the geomorphologist, ecologist and soil scientist often have natural phenomena as their study subjects. They may be looking at rock formation, plate tectonic, distribution of natural vegetation or soil units. Often, these entities do not have a clear-cut boundaries and there exists transition zone where one vegetation type, for instance, gradually replaced by another one. The application of GIS includes mapping location, quantities and densities, finding distances and mapping and monitoring change. Function of an information system is to improve one's ability to make decision. An information system is a chain of operation starting from planning, the observation and the collection of data to store and analysis of the data to the use of the derived information in some decision making processes. A GIS is an information system that is designed to work with the data referenced to spatial or the geographic coordinates. GIS is both database system with specific capability for spatially referenced data as well as a set of operation for working with data. There are three basic types of GIS application which might also represent stage of development of a single GIS application. Inventory application. Many times the first step in developing a GIS application is making an inventory of feature of a given geographic area. These features are represented in a GIS as layers or themes of data. The emphasis at this stage of application development consists of updating and simple data retrieval. The second application is the analysis application. Upon completion of the inventory stage, complex queries on multiple layers can be performed using spatial and aspatial analysis techniques. Management application. More advanced spatial and modeling techniques are required to support the decision of the managers and policy makers. This involves shift of emphasis from the basic geographic data handling to manipulation, analysis and modeling in order to solve the real world problems. 5 M's. There is quite simply a huge range of application of GIS. They include the topographic base mapping, socio-economic and environmental modeling, global modeling and education. The 5 M's of the GIS application are mapping, measurement, monitoring, modeling and management. In the very general terms, GIS application may be classified as traditional, developing and new. The traditional GIS application fields include military, government, education and utilities. The mid-90s saw the wide development of business uses such as banking, financial services, transportation, logistics, real estate and market analysis. The early years of the 21st century are seeking new forward-looking application areas in small office or home office and personal or consumer application as well as application concerned with security, intelligence and counter-terrorism measures. This is somewhat rough and ruddy classification. However, because of the application of some agencies such as utilities fall into more than one class. Many applications involve use of GIS by large number of people. Once a GIS application becomes established within an organization, usage often spreads widely. Integration of GIS with the Corporate Information System policy and with forward planning policy is essential prerequisite for success in many organizations. Government and public service, business and service planning, logistics and transportation, environment. GIS in environment. Environmental fields have long used GIS for a variety of applications that range from a simple inventory and query to a map analysis and overlays to complex spatial decision-making system. Examples include forest modeling, air water quality modeling and monitoring, environmental sensitivity zone mapping, analysis of interaction between economic, meteorological and hydrological and geological change. Typical data input into an environmental GIS includes elevation, forest cover, soil quality and hydrogeology coverage. In many cases, environmental GIS are used so that the environmental consideration can be better incorporated into socio-economic development, enabling a balance between the two. Biodiversity is receiving the attention of various scientists, planners, decision makers due to its importance as a natural reservoir with tremendous economic potential. Conversionists have focused attention on this fast depleting resource. In situ conversion using the ecosystem approach is popular, which also protects various ecological services offered by the forest ecosystem. The emphasis is on identifying the most valuable biodiversity hotspots that harbor non-timber forest species such as endangered flora and fauna, medical plants and wild relatives of cultivated crops. While identifying such hotspots, it is also important to take into account the land use and the human activities around the forest. Landscape ecology has benefited the most with the availability of spatial analysis tool like GIS. Landscape ecology considers vegetation as a mosaic of patches of vegetation with unique landform, species composition and disturbance gradient and focuses on parameters such as patch size, patch shape, patch isolation, relative importance of adjacent patches and fragmentation. All these parameters have a direct bearing on the status of biodiversity within the forest ecosystem. Spatial analytical capabilities of GIS allow the quantifying all the mentioned parameters with the remote sensing based vegetation type map. GIS is used to categorize the habitat of endangered animals using the elevated principles of landscape ecology. GIS in forestry. The use of GIS application in the field of environmental research has grown exponentially in the last decade. Originally, the focusing on forestry, the tools have been used for a wide variety of environmental projects from environmental research to forest fire prevention planning to protecting endangered species. With the tools available today and the increasing amount of data being compiled, the potential for new uses grow daily. Forestry involves the management of a broad range of natural resources within a forest area. In addition to timbers, forest provides such resources as grazing land for animals, wildlife habitat, water resources and recreational area. The Forest Service is responsible for management of forest harvesting, grazing leases, recreational areas, wildlife habitat, mining activities as well as protecting the endangered species. To balance the competing resource conversion and resource use, activities must be accommodated. Assessing the feasibility of these multiple uses is greatly enhanced by the use of GIS techniques. For example, the GIS for the Flathead National Forest in Montana includes digital terrain data, vegetation associations from Landsat satellite data, timber compartments, land types precipitation, land ownership, administrative district and the drainage network. GIS has been utilized for such analysis as timber harvesting, habitat protection and planning the location of scenic roads. GIS for fire prevention. Wildfire prevention efforts can be focused where wildfires pose the greatest risk of resource loss. When intense fire areas, that is highly flammable landscape, exist near high risk area, that is ignition sources, and high values, fire prevention becomes critical. Historical fire information can be viewed with all the other landscape information. Fire prevention officers can begin to determine an appropriate program strategy. This fire prevention strategy may be one of the education, enforcement or engineering depending on the type of land use and historical fire causes. As housing development continues to expand and encroach into wooded and bush covered areas, it becomes fire prone. The urban interface requires extensive fire prevention and fire protection measures. GIS can model and display potential fire prevention or the protection strategies. Forest fires have an important influence on the vegetation cover, animals, plants, soil, stream flow, air quality, microclimate and even general climate. The loss of timber is obvious and so is the damage to the life and property. The loss of recreation value of the forest and the destruction of the wildlife habitat are also the consequence of forest fires. Researchers and scientists have long been trying to predict the behavior of the forest fire. Computing modeling using high-resolution remote sensing satellite imagery, powerful software and GIS has been the efforts of many scientists in order to model a forest fire. The techniques for obtaining, analyzing and displaying the spatial information in a timely and cost-effective manner are needed. As forest fires are spatial, GIS is used as a tool for modeling. A fire simulation program called FIRE has been developed using ArcInfo. The model puts the power of comprehensive fire behavior prediction into the hands of qualified ground resource manager, where it can be most effectively applied. GIS for vegetation management. Landscape that require vegetation management treatments, for example, prescribed fire, mechanical treatment, will stand out when using GIS. Landscapes with high flammability characters, that is high hazard, high risk and high value, become obvious candidates for vegetation or fuel treatment programs. GIS technology allows fire managers to identify prescribed fire and vegetation management projects with highest benefit, that is meeting multiple goals for resource and fire management. Vegetation management tactics can include mechanical, chemical or prescribed burning techniques. GIS can assist in modeling how fire will behave and spread under a variety of conditions to assist in developing fire prescriptions. GIS in education and training. GIS is beneficial for education and training. Wildfire management personnels require several years of experience and training to become proficient. GIS provides us access to detailed landscape information during wildfire events. Fire personnels begin to understand the complexity, fire effects and fire behavior characteristics of various wildfires much sooner when using GIS. Modeling provides a better understanding of what a fire might do and what elements influence the wildfire most. Wildfire knowledge has traditionally been gained through years of experience, formal training and discussion with experienced fire personnel. GIS is now another resource fire personnel can use to expand their understanding of variables and complexity that affects wildfires. As modeling becomes more precise, dispatchers will be able to determine the potential of new starts and possible dispatch requirements. GIS is a vital tool for wildfire information management. GIS is a primary repository of information that can be quickly assessed and viewed when required. GIS becoming more suitable for emergency field operation use and is integrating tools that allow real-time display of information. Rapid access to information, safety, efficiency and better resource management decisions are being made with the use of GIS for wildfire management. Information is critical for wildland fire management. GIS information all in one place, easy to visualize and understand. GIS in health management. Public health management needs information on various aspects like the prevalence of diseases and the facilities that are available to take decisions on either creating infrastructure facility or for taking immediate action to handle the situation. These decisions have to be taken based on the observation made and the available data. Most epidemiological data have location and time reference. Advanced spatial analysis includes the combination of different data layers. Health authorities, for example, may be interested in the estimates of the number of children in a certain age group that may be exposed to malaria. Climate and topographical data can be used to determine the range of malaria mosquitoes. This range is unlikely to follow the Panchayat union boundaries, but in GIS, the two data layers can be combined to derive the number of children living within the affected areas in a particular Panchayat union. In short, the availability of statistical and other information in spatial referenced form and the functions provided by a GIS could allow analysis that were previously too expensive or impossible to perform. Geographic information system is an innovative technology ideal for generating data suitable for analysis, both with respect to space and time. GIS in hydrology. Over the last 2 decades, the dramatic increase in computer power available to the hydrologist has led to a significant development in a way that hydrological research and operations are conducted. Water resource application of GIS are concerned with the hydrological cycle and related processes. They are multifaceted because many of the problems involve interaction between the hydrosphere, atmosphere, lithosphere and biosphere. Solutions must serve competing group of users. Many of the important hydrological processes have local, regional, national and global dimensions. GIS technology allows for swift organization, quantification and interpretation of large quantities of geohydrological data with computer accuracy and minimal risk of human error. GIS in geology. Another field where the geographic information system is useful is a branch of geology. Geological interpretation is one area whether it is used in mineral and oil exploration or for engineering geological studies is principally a compound process of various data. The geologist or explorer linking different geological data will seek for useful geological structure in an area. All geological data, in order to be fruitful and productive, should be interpreted considering their geographic location. The geographic information system provides presentation facility and simultaneous data interpretation, enables the geologist or the explorer to prepare mineral potential maps with various data more quickly and precisely, which was impossible to be carried out with analog or traditional methods. The cartographic application of GIS in collecting, digitizing and preparing geological maps in different scales and on the national scale, that is geological, airborne geophysic, mineral, geomorphological maps are among the main application of the GIS for the numerous geoscientists. GIS in agriculture. Agriculture resources are among the most important renewable, dynamic natural resources. GIS software can help to integrate the data and can be used as the tool in precision agriculture application. Agricultural survey is the backbone of planning and allocation of the limited resources to the different sector of economy. Soil survey is an integral part of an effective agricultural research and advisory program. It provides complete information about soils and is an inventory of the soil resources of an area. It gives the information needed for planning land use and soil management program. Remote sensing and GIS are viewed as an efficient tool for irrigation water management. GIS in archaeology. Archaeological application of GIS have shown the little inclination to address time depth and historical factors. Several of the contributions are concerned with the use of GIS to manage and then analyze the archaeological data that is not collected explicitly for GIS. Anthropology and archaeology are disciplines that collect and use geospatial data. The field of archaeology in particular is now quite advanced in its use of GIS related technologies. Human adaptation and living patterns are affected by a variety of phenomena occurring at all levels of observation, from local environment and social condition at a micro scale to a continent-wide phenomena at a mega scale. GIS provides the potential to analyze affordable continental scale environmental data to study human adaptation patterns over large regions. A primary benefit of the GIS approach is that the data available for a variety of research users and the database is cumulative over time. GIS in fisheries. The dynamic nature of the marine environment presents many challenges to officials in charge of managing sustainable fishery. Traditionally, attempts to extrapolate spatial structure from aquatic environments have relied on very limited samples based primarily on catch information. With the advent of technologies such as Geographic Information System and remote sensing, fisheries managers and commercial operations alike have access to information that help them achieve their respective goal. As these technologies develop, it will be necessary to frequently assess the resulting positive and negative effects for both fishing industry and aquatic ecosystem. At present, the majority of the studies involving GIS application to fisheries have focused on minimizing cost for the fishing industry. However, it is equally important that these technologies should be applied during the stock assessment and policy determination. As accuracy and available data sets increases, so do the potential number of GIS application to fisheries. The increase in applicable data is largely due to the development in the field of remote sensing and satellite technology. Several countries have already incorporated these systems into GIS-based management plans. Buoys, satellite and other remote sensing technologies produce information on a large geographic scale. Satellite systems such as the Advanced Very High Resolution Radiometer AVHRR and the Coastal Zone Color Scanner CZCS have produced data regarding the ocean surface temperature and color, that is, the chlorophyll distribution, respectively. More recently, the satellites carrying the Sea Viewing Wide Field of View Sensor and Moderate Resolution Imaging Spectroradiometer (MODIS) have dramatically improved the spectral and spatial resolution of available imagery. Numerous fisheries applications for these data sets have been implemented and proposed for development. Summary: GIS application involve both natural and man-made entities. Examples are common in areas where we study the effect of human activity on the environment. Railroad construction is such an area. It may involve parcels to be reclaimed by government. It deals with environmental impact assessment and will usually be influenced by many restrictions such as not crossing seasonally flooded lands and staying within inclination extremes in hilly terrains. The second distinction in application of GIS stems from the overall purposes of use of the system. A prototypical use of GIS is that research project with an explicitly defined project objective. Such projects usually have a priori defined duration. Feasibility studies like site suitability, but also stimulation studies, for instance in erosion modeling, are examples. We call all of these projects-based GIS application. In contrast to these are the institutional GIS application. They can be characterized in various ways. The lifetime duration of these applications is either indefinite or at least not a priori defined. Their goal is usually to provide base data to others, not to address a single research issue. Good example of this category are monitoring system like early warning system for food, water scarcity, or the system that keep track of weather pattern. Indeed, our El Nino example is the best qualified under this, because the SST and WS measurements continue. Another class of example is found in governmental agencies like National Topographic Surveys, Cadastral Organization and National Census Bureau. They see it as their task to administer geographic changes and their main business is to stay up to date and provide data to others in the form of printed materials such as map or in the form of digital data.